Hello guys, so today we're going to be discussing a couple of really interesting things. One is functional equations obviously, and when you combine that with the modulus function. So anyway, it's going to be like an intersection of a little bit of algebra and calculus. So yeah, this is quite an interesting problem, and let's start. This is problem number 8 from the ISI Entrance Exam in 2015, so last problem of the exam. And in this video, we're going to be discussing modulus functions, functional equations, some interesting observations and geometrical interpretations, the cheat solution, right? Book suggestions for ISI and CMI, and at the end, a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so what does it say? It says us to find all functions f mapping from reals to reals such that the modulus of this thing is twice of mod x minus y, right? So modulus, I'm sure you're aware of it. So modulus of, let's say, 2.3 is 2.3. It essentially converts any negative number into positive, right? The output is essentially always positive. So for example, mod x, more formally, mod x is essentially x if x is greater than or equal to 0, and mod x is actually negative x if x is less than 0. There's maybe just some formal things that that are good to know. But in this question particularly, they've given us this modulus of f of x minus f of y, right, is equal to twice of mod of x minus y. Okay, great. So what can we do? So now I'm probably going to discuss an important concept called as injectivity, right? Injectivity, right? So what is injectivity? The property is called as injectivity, and the functions that follow it are called injective functions. So let's say for any function, so for a function f, if f of a is equal to f of b, and that implies a is equal to b, then f is said to be injective. Okay, so so for any function in general, if f of a is equal to f of b, and that necessarily implies that a is equal to b, then f is said to be injective, right? One on one. Great. So let's try to maybe prove a little bit of injectivity over here. Maybe let's try to see if the function is injective or not. So here what I'm going to do is I'm going to let f of a is equal to f of b, and after I take this assumption, if I'm able to conclude that a is equal to b, then f is obviously injective, right? F is an injective function. Great. So now that I've assumed this f is equal to f of b, I'm going to plug in x equal to a and y is equal to b. And when I plug that into the functional equation, I get modulus of f of a minus f of b is equal to twice of a minus b. And since f of a is equal to f of b, so this is obviously 0. So twice of mod a minus b is equal to 0. Mod a minus b is equal to 0. And the only way this can happen is if a is equal to b. So essentially, we assumed f of a is equal to f of b, and then we implied that a is equal to b. So therefore, I can comfortably write that f is injective. Right? We can essentially say that f is injective. Great. Now there's actually an interesting observation. The observation is that if f of x is a solution, then f of x plus c is also a solution. And how do we prove that? Well, it's kind of intuitive actually. You can just maybe intuition works a lot of way, but maybe let's just discuss a little bit of a formal proof of it. Let's just see why it works. Right? Let's just try and maybe prove that. So proof, now what I'm going to do is I'm going to define g of x is equal to f of x minus f of 0. So if I plug in x equal to 0 over here, I'll get g of 0 is equal to f of 0 minus f of 0. So g of 0 is 0. Right? This is a result that we can easily conclude from here. Now what do we have over here? So f of x is essentially g of x plus g of 0. Right? What is f of y? It will be nothing but g of y plus g of 0. Great. So f of x minus f of y will be nothing but g of x minus g of y, right? Because these two things will be cancelled, is equal to twice of mod x minus y. Okay, that's great. Now I'm going to just plug in y is equal to 0 and x equal to x. Simple substitution. So I'll get mod of g of x minus g of 0, which is 0, is equal to twice of mod x. So essentially, when I have mod of g of x is equal to twice of mod x, so therefore g of x has to be plus or minus 2x. Right? So g of x has to be plus or minus 2x, because when you take mod, everything becomes positive anyways. So g of x has to be plus or minus 2x. Now what is f of x? F of x is g of x plus f of 0. Right? So what will be f of x plus or minus 2x plus f of 0? And what is f of 0? F of 0 is nothing but a constant, right? You plug in 0 into the function, you'll obviously get a constant value. So f of x is equal to plus or minus 2x plus c. Right? So f of x can either be 2x plus c, or it can be negative 2x plus c. Right? Now, well, this is good up to this point, but like you discussed many times before, there's this pointwise trap, that keeps coming in the middle, and it can really mess up a lot of things. So maybe let's try and discuss that also. It's quite trivial. The method is again same as always, but let's just discuss that. So we got g of x equal to plus or minus 2x. Now let's say for some a comma b, g of a is not equal to 2a and g of b is not equal to minus 2b. That essentially means that g of a is equal to negative 2a and g of b is 2b. Right? Pretty simple. And now when I just plug that back into the functional equation, I'll just put in like x equals to a and y is equal to b. And when I do that, I'll get g of a minus g of b, and the modulus, of course, equal to twice of mod a minus b. And what if g of a is negative 2a and g of b is negative 2b? This is twice of mod a minus b. The 2 and 2 get cancelled. So mod of negative a negative b is equal to mod of a minus b. And this is only possible if a is equal to 0 or b is equal to 0. Because you see, when a is equal to 0, I'll get mod of negative b is equal to this thing. That's absolutely true, right? Because both the sign will be same when you open it. And otherwise, if b is 0, then I'll get mod of negative a is equal to mod of a. Which is again true. Both will again open in positive, so it won't make any difference. So essentially, the conclusion that we can find is this can only be true if and only if a is equal to 0 or b is equal to 0. But we had essentially assumed that g of a is negative 2a and g of a is not 2a. Similarly, we had assumed g of b to be 2b and g of b to not be negative 2b, right? And here we're essentially saying that a has to be 0 or b has to be 0. So if a is 0, then we get g of 0 is equal to 0, and we get again g of b 0 is not equal to 0. And if b is equal to 0, we get g of 0 is 0, and here we get g of 0 is not equal to 0. In both cases, we get a contradiction. Right? As simple as that. In both cases, we get a contradiction. Therefore, it is not piecewise. G is not piecewise. Right? So essentially, g of x equals to plus or minus 2x for all x. That's essentially what we had intended to prove. And yes, from that we derived value of f of x, which we had to find, which is plus or minus 2x plus c. Okay, great. So this is kind of an interesting thing. And another thing that you can maybe note is Lagrange's mean value theorem. So what I was talking about earlier was like a cheat solution, right? Cheat solution. What is a cheat solution? Cheat solution is obviously not a perfectly correct solution, but if you do this, maybe you can get a kind of like a good idea of how to proceed with the actual solution, with the formal solution. So to know the cheat solution, let's first discuss Lagrange's mean value theorem. Lagrange mean value theorem, and this is commonly known as LMVT, right? So it's a pretty famous theorem on the application of derivatives, and it states that if a function f is continuous, in a to b, right? Keep in mind this is the closed interval and differentiable in the open interval a to b, right? Then it says that there exists x equals to c such that f prime c is equal to fb minus fa divided by b minus a. This is what Lagrange mean value theorem says, and it consists like a geometrical proof or something, which is kind of important for this question as well. It's quite interesting if you check that out. But if you actually check the question, what was the question? It was mod of f of x minus f of y is equal to twice mod x minus y. And you know what really happens over here is I can just rewrite this as this, right? Mod of this thing divided by mod of x minus y is equal to 2. So essentially f prime c is taking the value of 2, and pretty much we have similar things like this, other than the fact that we have a modulus sign over here. So essentially f of x minus f of y divided by x minus y, right, is equal to plus of minus 2. And what is this? This is nothing but f prime of x, right? F prime of x is 2 plus or minus 2. And if I just integrate that on both sides, I get f of x equal to plus minus 2 plus c, 2x plus c. Right? It's just simple integration. But here's the thing. So we got f of x equal to plus minus 2x plus c, right? From the earlier, our formal solution, which is the correct solution, of course, we also got f of x equal to plus minus 2x plus c. So could you have done this in the exam? This seems a lot simpler. You know, this configuration, when you look at this question, the first thing that comes to mind is Lagrange mean value theorem. Like, literally, that's like probably one of the most first things that clicks to your mind if you study calculus. But here's the thing, they've not given that f is differentiable, right? In the question, nowhere is it said that f is continuous, f is differentiable. No, nothing, no such information is given, right? Okay, from the conclusion, you found that f is a polynomial function, so it's differentiable and all that. But essentially, in the question, it's not given that f is differentiable. So if f is not differentiable, then kind of like the assumptions of this LMVT fails, right? It has to be differentiable. But it's not given the question, so obviously you cannot employ this as your formal solution. However, it gives you a good idea. It pretty much gives you the answer right up. You know, this thing, that observation that if f of x is a solution, then f of x plus c is also a solution. This can be easily checked out by this. Right? When you see this, you get the idea that f of x is a solution, f of x plus c is a solution, because you have plus c over here as well. Right? So this is why this maybe like this kind of like interpretation is quite important. But yeah, essentially, when solving this, you can actually prove that f is differentiable if you make certain additional arguments, but you can't just directly use this because it's not given that f is differentiable in the question. But yeah, you can definitely follow this formal solution above that we provided, and yeah, please maybe like this intuition that if f of x is a solution, then f of x plus c is also a solution. This is also pretty good. We proved that obviously. But if you actually apply Rolle's, Lagrange mean value theorem over here, you can see that pretty well from here as well. So yeah, anyways, I hope you enjoyed that, and let's move on. Okay, so we have certain book suggestions for calculus and ISS-EMI. Pre-calculus by Tarasov, single variable calculus by I. Maron, playing with graphs, challenges and thrills of pre-college mathematics, mathematical circles, excursion mathematics, and a test of mathematics at 10+2 level. Okay, so we have a similar but challenging problem. And in this, I wanted to determine the number of increasing functions for which modulus of f of x minus f of y is less than or equal to x minus y, mod of x minus y. An increasing function is a function which is obviously always increasing. So if f of x is greater than f of y, then that necessarily means that x is greater than y, right? This is essentially an increasing function. So determine the number of such functions for which this condition essentially holds. And yes, if you're able to make any progress on it, or if you're able to solve it, let me know in the comment section. Until then, I'll see you in the next video. Thank you very much, and bye-bye.
The programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.